Hello class, my name is Professor Ben T. Gad, and today we're going to be talking about lasers. Does anyone know what laser stands for?
Oh, I know. Looking at the sun and erasing your retinas.
No. Anyone else? Light amplification by stimulated emission of radiation. Yes, that is quite impressive. And today we'll be talking about each of these parts individually and also about some applications of lasers.
L, the first letter in our acronym, stands for light. Light is made up of photons which exhibit both wave and particle-like characteristics. Photons also carry energy with them, given by this following equation, where E is the energy of the photon, H is Planck's constant, C is the speed of light in a vacuum, and lambda naught is the wavelength of radiation in a vacuum.
Okay, so the A in laser stands for amplification. Amplified entities have to be identical in all aspects, including energy, polarization, momentum, and phase. As you can see, we start with 1 John Cena and we end up with 9 John Cenas, all identical.
So we're on to SER, which stands for stimulated emission of radiation. Electrons at their ground state can be excited up to a higher energy state by absorbing external energy. Under normal circumstances, these electrons will decay spontaneously, releasing photons with random direction and polarization. However, in stimulated emission of radiation, we can hit these excited electrons with a stimulation photon, causing them to decay back to their ground state and creating 2 photons with identical properties. An important part of efficient lasing is population inversion, in which a pumping process takes many electrons at their ground state and brings them up to a higher energy state.
Laser cavities increase the efficiency of laser systems by providing optical feedback for stimulated emission. The lacing medium must have a low concentration of doping material so that light can still pass through it. For this reason, the odds of interaction between a stimulated photon and an excited electron are low. In order to increase this probability of interaction, mirrors are placed on either side of the lacing medium so that stimulation photons can bounce back and forth multiple times, increasing the likelihood of an interaction. One mirror is only partially reflecting so that stimulated photons are allowed to pass through. Lasers have many uses in many different fields. For example, in the surgical field, lasers are used to treat kidney stones and correct bad vision. In the commercial field, lasers are used in optical disc readers such as CD drives and laser printers. And finally, in the industrial field, lasers are used to cut and weld materials and are also used in direct laser writing, which is the process of creating microscopic structures, such as the woodpile structure.
So that's it for today's class. Any questions? No? All right. Well, I'll see you all next time. Oh. That has been an introduction to lasers. Can't work like this.